All right, good morning. So, we are going to continue on talking about more ways to do things with alkenes. Yesterday, we looked at Markovnikov and anti-Markovnikov ways to halogenate compounds, hydrohalogenation. We saw that in the presence of peroxide, a radical mechanism is preferred and you get the anti-Markovnikov product if you're using HBr. HCl and HI don't work. They would still follow Markovnikov rules. And then we saw that just putting in any of your acid, not acid halides, hydrogen halides, there we go, you'll end up with the Markovnikov product, where you end up giving your hydrogen to the side that has more hydrogens, and you will put your substituent on the more substituted carbon. So we're going to see here now. Um, Actually, then we did one more where we did we did we do I think we did water adding to, yeah, we did. Okay, so water, if we use acid with water, you can get a Markovnikov hydroxylation. However, you do have a carbocation present in this mechanism, and so there's the potential for rearrangements. So we're going to learn, oops, I guess I started this. We're going to learn now how to do this. We're going to learn a Markovnikov hydroxylation without the carbocation. So we'll see the carbocation one is great. It works if we don't have rearrangements possible. However, if we do have, I just totally realized I spelled this guy's name wrong, didn't I? There we go. We'll do it without making that carbocation. This one was called oxymercuration, demercuration. So let's take a look at what's going to happen here. We're going to see that if we just tried, say we had a something like this, where we have, if we were to try and do H3O plus on this, we would end up with our major product putting the alcohol on that tertiary carbon. But we're going to see that if we use a different set of reagents, mercury 2 acetate, along with water. So first step, we're going to use the mercury here, and then we're going ahead and use water. And we're going to see that with a nucleophile, it's going to be a nice way to do it. And then we're going to end up needing to do a second step where we are going to use NaPH4. And then we're going to end up getting our alcohol, our hydroxy group in here. Let me condense these. We'll make it a little bit easier. We're going to end up with our hydroxy group in the Markovnikov position, as in the more substituted side of that alkene, without it rearranging and forming a carbocation. So we'll end up with it directly onto where the alkene used to be. So there's a lot of important considerations to take. Do we want our oxygen to end up in a different place? Do we want it to be on this position directly? That's the choice we must make. So if you want to do the anti-Markov or the Markovnikov hydroxylation without a carbocation, you'll use oxymercuration, demercuration. And let's take a look at what happens here. We're going to see that really the active species, these are acetates, acetic acids. If I were to draw them out, whoops, that's what AC means, acetate. What really happens is we don't really see this as is directly. We see it as having the positive charge. That's the reactive species. And then you have the acetate ion. All right, again, I can write this as ACO. We like to use abbreviations in OChem. So, as you've probably seen, so this is the active species that we're going to be looking at here. This active species is going to come and have some interactions with our alkene. Alkene was this. So it's going to end up creating a bond along that double bond, right? So remember we saw that the double bond can act as a nucleophile. And as a result, what we're going to end up seeing is we remember that the less substituted side of the alkene is the more nucleophilic side. So we're going to have a stronger bond to Hg and a weaker bond on the other side. So it's just going to kind of, I don't want to say it's going to attack, but it's kind of like we're going to have this attack, and then it's going to attack right back. Actually, it's going to attack the other side. So I should draw my lone pair on the other side. Mercury has the s electrons, right? So it has the lone pair. It really is essentially attacking and being attacked at the same time. So we can see that it's going to form this kind of triangular cyclic compound, and I'm going to make this really exaggerated. So I'm exaggerating this bond, illustrating that we have kind of a weaker bond here. Because of the nature of how this reaction is taking place. Mercury, I mean, it's not really one to make that many covalent bonds, right? But we're going to see that because Mercury is kind of special, it's a metal. Metals make different types of bonds than covalent things do, right? So what actually happens here is because this bond is a little bit weaker, we're going to see that we sometimes will draw it as a dotted bond, and we'll see that we'll have a partial positive on that carbon because it's going to be a little bit electron deficient, right? We don't really see mercury as a nucleophile, right? It's a metal. It's more likely to be electron deficient than electron donating. But if you want the mechanism, yeah, it's using its lone pair to go ahead and latch on there. But in reality, it's more a kind of a partial bond. So as a result, we end up with the weaker side really having a partial positive on that carbon. The partial positive is going to end up on the more substituted carbon. That's the important bit here of the two of the alkene. And so I realize I've just blocked off exactly where I wanted to write. Um, we're going to have our water. Notice we had water in our mechanism. That's part of our reactants. Water's going to come in, attack that partially positive. This is a nucleophilic attack. And that weak bond is going to be broken, and the electrons are going to go back onto Mercury. And what we see here is now we have our water having attacked, so now it's stuck on there, and we've kind of broken that three-membered ring thing that we had before. It's Bailey, what are you doing over there? So our nucleophile has attacked, and we're going to see now that we can go ahead and have the acetate come in here. The acetate that was kicked out before, that's this acetate right here, is going to act as a base, and it's going to just help deprotonate this thing. Acetate's a weak base. And so we end up with now this OH, and then we've got our mercury covalently bonded to the carbon. That's step one. Step two, we're adding sodium borohydride. That's a reducing agent where we're going to have H minus as a nucleophile. So we still have this now relatively electrophilic spot. Because it's bonded to a metal, right? It's not quite there. So we're going to see that BH4 will donate a hydrogen, and it's going to kick out our mercury, which leads us to our product. So it's going to donate a hydride. All right, so we end up with our OH here. We now have an H, and then we have the rest of our molecule. And of course, the H we typically don't draw, but I should be more consistent. I'm going to draw it down on this side, just so we can see something important later. So the NABH4 is a reducing agent. And its purpose there is to deliver H minus as a nucleophile. H minus, if you just tried potassium hydride, it's not a nucleophile. It's much more likely going to act as a base. H minus is a very good base because it produces H2 gas, and that just bubbles away. And as a result, Le Chatelier's principle, equilibrium, pushes the reaction further. So H minus is a base, an irreversible base. But NABH4 kind of tames down the basicity of it and allows it to act as a nucleophile instead. So you can't just use KH or something like that, or NaH. Those will not act as nucleophiles. I'll write that here. That'll be important later on. So you can't just use KH, you have to use NABH4. There are other reducing agents you can use, but this is the most common one, and it's the safest. So that's what we're looking at here. So let's take a look at the entire mechanism and let's go through it. So first step is we have our mercury, and it's going to dissociate, forming one of the acidates will leave, essentially. That mercury then becomes attacked by the uh, alkene, and it will attack the alkene in return. The bond that it forms by attacking the other side of the alkene is weaker, so it has a delta positive because it's not as strong of a bond, it's only a partial bond. That spot is open to nucleophilic attack. So we have water or some other nucleophile present, and then we can go ahead and deprotonate. And then we use a reducing agent, such as sodium borohydride, to attack and remove the mercury from our compound. That is the demercuration step. So up to that point, we had an oxymercuration. So we added an oxygen and the mercury. And then to demercurate our compound, we have to get rid of the mercury using the reducing agent. All right, so that's what we end up seeing for this reaction. And overall, again, what happens is we take an alkene and we get a Markovnikov hydroxylation without the formation of a carbocation. So we kind of form this partial carbocation, but it's not able to migrate because it's not a real carbocation. So that's the benefit here. All right, let's go this way. So, cool. All right, and then we end up kicking out our mercury, and then we're good to go. So, let's take a look at another thing we could do. If we did the same reaction with, say, ethanol instead as our nucleophile, we would get something similar. We would get an ether instead. If we want to look at this would be called alkoxymercuration. Demercuration. And so we can use this to, instead of putting an OH, put an OET on, make an ether instead. So that's one other thing we can do with this. And the mechanism is exactly the same, except instead of having water attack in this step, you'd have ethanol attack. The oxygen on ethanol would attack, and you'd deprotonate it just like before, and everything else happens the same way. So you can do this with other nucleophiles as well. Typically, water or an alcohol are the more common ones. So alkoxymercuration uses an alcohol instead of water. All right, but the rest of it's the same. The mechanism is exactly the same as well. So same thing. You'll get an anti-Markovnikov. I'm sorry, not anti. It is a regular Markovnikov ether that you end up with. And again, this will end up being a racemic mixture, just like your alcohol was. Important thing to note, though, is that this is a Syn addition. I'm going to note that. Both of these reactions Syn means same side. I don't know if you noticed, but I very carefully put the hydrogen that's added on the bottom, the same side as your OH goes. While that's not terribly important right now, we can have some important things if this was a chiral compound, or if it could make, a second stereocenter. Okay. If we do this one, we can go crazy with this. Let's not. No, this is a bad example. We'll have better examples of Syn additions later on, so we'll focus on that later on. The important point is that both of them attack from the same side. So your water, if it's attacking from below, your hydride will also attack from below. It's a Syn addition. They both attack from the same side of the alkene. Recall that all alkenes are planar. And so I'm going to switch over to Google so I can show you what we mean by that. And so when they're planar, we're going to see we can attack from either the top or the bottom. And a Syn addition will have will have both of them attack from the same side. Let's see if we can't get some nice images of what this looks like. These are kind of, show me some like mirrors. Here we go. Okay. So let's switch over to this screen here. With Syn addition, lovely. Okay, so alkenes are planar. So we can either, I mean, this is a hydrogenation. This is a reaction we'll look at next, actually. We can either attack from the top, which pushes our other substituents down, but notice they're both on the same side, right? So we're adding H2 to this molecule. We're going to see that we can have these, they're going to both end up on the same side of where that alkene was. Alkenes are planar, so you can add from the top. If you add from the top, you get this particular isomer, stereoisomer. If you attack from the bottom, you end up with the enantiomer of it. So with Syn additions, you're only going to end up with a pair of enantiomers. And let's see if we have some anti-addition. Yeah. So if we had an anti-addition, we have one thing from the top, one thing from the bottom. That's going to be different from Syn. We get a different mix of stereoisomers. So interestingly enough, this compound on the bottom right is meso, so you in fact only get one compound out. But with this one, you would get the anti-product, and you can get either enantiomer. You can either have the wedge on the bottom, dash on the top, or vice versa, depending which one attacks from the top, which from the bottom. So Syn addition means they're both added to the same side. All right, anti-addition means you're going to add them to opposite sides. All right, so let's look at this a little bit more. Oh my God, did I not? Did I show the screen? Oh well. Oh, I hope I did. I think I did. So this is the Syn addition. So it's going to attack to this. Okay, good. Oh, hey, Kevin. So Syn addition, it attacks from the same side of the alkene. It may not look like it, but consider what we have here. We have our mercury forming this cyclic intermediate. Water attacks from below, SN2 style. Attacks from the less hindered side, right? Attacks from behind. And that ends up putting it anti to the mercury. But in order to get the mercury to leave, we have to do an SN2 on the mercury. So as a result, we are still adding both to the same side. So this is an example of a Syn addition. So both of these would add to the same side of our molecule. It's not really relevant here because the hydrogen side is not chiral. So typically we don't worry about that. And this one is less important to worry about because if you were to use a tetrasubstituted alkene, it'd be hard to say which side you're going to put the alcohol on because Markovnikov rule says you're going to put it on the more substituted side, but if they're equally substituted, what do? You get a mixture. So a little bit tougher to show, but we'll show that with the next, not the next reaction, but one after that. Alrighty. So this was Markovnikov hydroxylation without a carbocation. You can get Markovnikov hydroxylation with a carbocation if you just use acid and water. So let's look at another one. How do we do the anti-Markovnikov? Hydroxylation. This is a reaction called hydroboration, oxidation. And the reagents that we're going to need for this one are borane. Usually the solvent is tetrahydrofuran, so I'll show you what those two structures look like. And then you use NaOH and hydrogen peroxide. And you'll end up hydroxylating your anti-Markovnikov position. All right, again, this would be racemic. All right, so let's take a look at these. We have borane, and then you have tetrahydrofuran. Tetrahydrofuran, THF. The THF is here to stabilize borane, because borane has an empty p orbital. It only has 6 electrons for its octet, right? So what actually happens is you have THF kind of stabilizing it, borane here. Otherwise, you end up with dimers of borane, and they're going to become not reactive. So we're going to see that these two form a complex that's going to be the more useful species. So if your oxygen on your THF, which is your solvent, it's an ether. Ethers are typically solvents. Just goes ahead and attacks, you end up with this complex, which is going to be our reactive species. So we're going to go ahead and take a look at what's going to happen here. So we're going to see that this is going to be another Syn addition, and we're going to go ahead and look at what's going to happen here. So with this, this is just going to stabilize the borane, preventing it from making dimers with itself. Borane dimers look like this, by the way. Oops, too many. It's interesting when they form dimers with each other. You have two boranes, and they kind of make this weird shared hydrogen bond thing. There are only 2 electrons still. This is diborane. This is not a reactive species here. So like these bonds are shared between the borons. There's still only 2 electrons because hydrogen can never have more than 2 electrons, but we could still draw it this way. And so it's kind of better to maybe just draw them like this. Maybe that would make it a little bit more clear. So you end up making dimers of them, which is not going to be very reactive here. This is more stabilized as the single borane. So let's go ahead and see what this is going to look like. If we have our alkene and our borane, and I'm going to just draw the borane as if it were not stabilized, as it were, if that's all right. We're going to see that really we're going to have our, we're going to kind of make the similar idea here of having the boron kind of take a seat on a sit on top of the uh, molecule here. So in, I'm sorry, this is not a very clear arrow. Let's make that super clear. So what happens with this? Shall we go down? Yes. We're going to have the carbon attached to the boron. We're going to have one of its H's attached to the other side of the alkane. Alkane is no longer there, I should say. Notice this is a Syn addition. We're attacking from the same side. We're going to have this attack our boron. One of the boron hydrogen bonds ends up coming in here. I'm okay, by the way, if you just use BH3 as your reagent, but it's really stabilized by the THF, so I'm just showing that as well. So either way, you're okay. So we have a Syn addition here, and we end up with our hydroboration. So we add a hydrogen, and we add the boron side of things here. So that's step one. That's the hydroboration step. The next step is the oxidation. And in order to do that, we have to look at what our reactive species is going to be. And it's going to be the peroxide ion, hydroperoxide, I guess we could say. And that's going to come in here, and it's going to kick out our boron. Technically, technically speaking, we're going to actually oxidize our boron as well. But I'm sorry, this is not the right nucleophile. We can just use the OH here to end up kicking this thing out. So we're going to see that the boron technically is going to be activated first by being attacked by all these peroxides. So let's do that first because it's going to become a better leaving group. We're going to end up having the boron attacked by the peroxide ions. Let me just move this thing down here, just so I have a little bit more space. I know that this mechanism is a bit long, so we're going to have to show it kind of each little bit. So here we go. This step is going to happen multiple times. So our boron, because it has that empty p orbital, gets attacked by our peroxide. And that's going to be the kind of important step here, because what happens, I'm going to redraw this. I'm going to ignore the H for now. That's already there. And then we had two H's on this thing. So we end up with this intermediate. We're going to end up actually migrating one of our hydrogens onto it, and that's going to end up leaving. So let's go ahead and show that step here. So we're going to end up having our hydrogen move over. The boron is going to, or here we go. So that's going to end up moving over there onto the oxygen, and we're going to end up kicking out our other oxygen. So with this step is going to happen multiple times, and we're going to see this later when we talk about alkynes. And then we will produce another OH minus. Not a very good leaving group, but we'll be okay with that, because we're going to need the OH minus to kick things out anyway. We're going to do it again. It's going to come in, attack the boron. I'm sorry, I'm going to be consistent with my colorful arrows. Does it again. Fun stuff. We end up getting this over and over and over again. Eventually, we end up with the last one. We'll see. The last step will be the important one. Let's show each one. O, OH, H minus. Kick this out. All right, here we go. We are finally ready to make this happen. So, okay, so we have now two of ours. Let me draw it another way, sorry. Okay, we're almost ready to make this happen. One more time. It's on. All right, get ready for it. Here we go. This is the important step here. This is where we're going to get our thing to move. So previously we had moved all those hydrogens away. This time we're going to move the rest of the molecule, the part that is uh, weirdly on that side. So we're going to move now the rest of it. We've moved all those hydrides away, producing OH each time. The OH goes and reacts to make the peroxide ion. And now, finally, we end up with our our hydroxylated species. So technically it's O minus, and then it's going to go grab a proton from water or something. Here we go. Grabs the proton, and now we have our species of interest. I've drawn these all, each time I drew the OH, we're kicking out, we've moved the OHs around, right? Oh wait, no, I'm sorry. I have one more step to do. We just have to have it leave, and then it's going to technically then just get protonated. So we'll just leave it like this. Cool. Technically, we still have the boron hanging around here, and technically, it's still on our species. So I should really be. I hate these boron mechanisms because they're 15 steps long, um, and they take forever. So we'll just be super. I'm going to make this super clear what's happening. We have our boron here. Another peroxide comes and attacks it. We have to actually get rid of it. So that's the part that's missing still. Oh my gosh, I hate these mechanisms. All right. All right. So we've got now boron. I'm going to draw on the other side actually. OH, OH, and OOH. Or it can be attacked by OH, we'll say. Doesn't really matter. The point is, once it has four things on it, we're then going to just decouple it. Could be OH instead, doesn't really matter. Now we decouple, and now we can protonate. What a mechanism. This thing just takes forever. And we end up with this. All right, and then we get thing. So let's use just hydroxide as this other one. It'll just be easier. We don't have to worry about that step. So we'll just have OH attack here. So nasty mechanism. Let's take a look at the whole thing and let's see what's happening each step of the way. So honestly, the hydroboration part is not a problem. What happens, you have your boron come in along with the hydrogen. Done. Syn addition. Next, we have all these peroxides attacking repeatedly, repeatedly. They migrate hydrogens over to themselves, kicking out OH minus. That happens a few times. On the third time, we end up migrating the rest of our molecule onto the oxygen. We have a final hydroxide attack. Once the boron has four things, it's ready to let go of our negatively charged alkoxide, which then can protonate itself. So many steps for this. So many steps. And then the last step is just kind of the protonation, right? So we lose a leaving group, the O, the rest of our molecule of interest, and we end up producing our final alcohol, and we lose this trihydroxyboron. Ooh, what a mess, right? We're going to see when we talk about alkyne reactions, we're going to have something similar happening with all these boron reagents. So the whole point of that was to do a Syn addition of an anti-Markovnikov hydroxylation. So this was an anti-Markovnikov hydroxylation. That's all it is. All right, the mechanism is to show you what's happening with these reagents. And so that's this part here. For predicting the products, though, it's simply all you really need to focus on is putting on the hydroxy group in the anti-Markovnikov position. So, fun stuff. I always struggle with that. There's so many freaking boron attacks that it's just annoying. So that's what we end up getting here. So another Syn addition that we're going to end up getting, and we get the enantiomers here. All right. Questions on that one? So puts on a hydroxy group in the anti-Markovnikov position. So the less substituted side. More substituted gets your hydrogen, and then the boron goes to the less substituted and eventually will be replaced by an OH. Eventually, after 200 steps of mechanism. Cool. Fun. So let's look now at hydrogenation. We'll just keep on going. Hydrogenation is going to be a Syn addition of hydrogen gas. You need a catalyst to get this to happen. Usually that catalyst is platinum on carbon or palladium on carbon. These catalysts will set the surface for us to have our reaction take place. These are what are called heterogeneous catalysts, aka insoluble. And they're going to provide a surface for this reaction to take place. We're going to see that, let's see, let's make this actually have some chirality here. The platinum on carbon, if we do this, we're going to get some products here. We're going to get the enantiomers of these two. Although this is going to be meso anyway, but we're going to see here that we'll end up with theoretically a pair of enantiomers, depending on if we have attack from the top or attack from the bottom. And how this works is you're going to have your catalyst, which will be your platinum, seated on carbon. The reason for that is because carbon has got very good surface area, and you're going to just see these little platinum. You're going to kind of coat that carbon with platinum, so you have a high surface area. What happens is you have H2 molecules kind of just sitting on this platinum. And it's there to just keep things, or to get things to be attracted to each other. So we're going to have our alkene come around there as well. I don't know why I drew like ball and stick model. But the catalyst is just the surface there to help this to happen. So you end up putting one H on one side and one H on the other side, and because they're coming entirely as a molecule right next to each other, it's going to be a Syn addition. So if we're coming from the bottom, we might have this bit here. So in either case, you get an a Syn addition, and you can get either from the top or from the bottom. And again, thankfully, this random thing I found on Google was helpful for this. So we'll go ahead and look at that again. So with a Syn addition, we have our molecule either coming from bottom or top, either way, and you end up with the enantiomers, which may or may not be meso. Just depends on what your structure looks like. So in this case, on this example, we have a methyl on one side and ethyl on the other, and deuteriums on the other sides. So this will not be a meso compound, but it will be still Syn addition. So you will end up with enantiomers, depending whether your hydrogen attacks from the bottom or the top, and you're going to end up with a racemic mixture of the two. All right, so we'll have that there. So that would be the Syn addition onto our catalyst here. All right, so hooray. So we're going to end up getting that catalytic hydrogenation to happen. And there are more advanced methods to get them to form a single enantiomer, but we don't really focus on that at this level. In more advanced organic chemistry, you'll focus on getting a single enantiomer out. In fact, I wonder if I have it. Let me see. Oh, I do. This is a book I used a while ago. Enantioselective chemical synthesis. Hooray. So you'll have all sorts of fun ways to do hydrogenation, or some of these additions to alkenes to form one enantiomer only. And let me just show you how complex some of these things are. It's like, oh, let's just use these crazy catalysts. And you end up with these very complex, very large catalytic molecules to end up putting these on here. Let's see if I can find you some examples of, those are to imines. Let's see if we can get some reduction of CC bonds here. These are to carbonyls. Wow, so many to carbonyls. Aha! Oh no, those are... Okay, here we go. So, these are so many different ways to get enantioselective modes of hydrogenating alkenes. So you can see here we have all sorts of crazy catalysts. Like, look at how complex some of these molecules are. Here's one of the catalysts. I don't know if you can see how big it is. You have these, is that a binap? Yeah, it's a binaphthalene derivative. So if you have chiral catalysts present, you can get these to happen. And so these are all reported reactions of people doing these hydrogenations to form a single enantiomer. So it can get very complex. Platinum over carbon is basic catalyst. If you have these crazy, huge catalysts, you can get these things to go on just one enantiomer. But for right now, that doesn't matter because this is meso anyway, so we're okay. But for other ones, there are ways to do it. So, but for us, we don't have to worry about that. This is 221. We're baby organic chemists, so we don't have to worry about that yet. All right, let's talk about halogenation. This is our first anti-process. Effectively X2, we can say. This is why we can't do our allylic. It's hard to do an allylic radical reaction with a halogen. We need to use NBS to do that. We're going to see that, well, this is the side with the double bond on. We're going to end up with having them on the opposite sides when we halogenate an alkene. We're going to end up having, in this case, we're still going to have the enantiomer, but we're going to have them anti to each other. It's an anti-addition. So if you were to try and do a Syn addition would have a different set of have the opposite set of enantiomers. We have two chiral centers here. Actually, we don't, because the one on the right is not chiral. But okay, fine. We're gonna make it chiral. Boom. Now it's chiral. Okay, so if you do a Syn addition to this molecule, which is not something we're going to see right now, we would end up with the opposite set of enantiomers, right? We would have either both dash or both wedge with an anti-addition, which is what we're going to focus on. That's going to have one on a wedge, one on a dash. All right, everything else the same. So we're going to not worry about these right now because we're going to look at anti-addition. So let's take a look at how this works. And let's use bromine because that's our favorite halogen, right? That's typically what this is done with. You can use chlorine though, but bromine's a liquid. It's easier to use. So we're going to go ahead and use bromine. So all right, I'm going to actually move this down just a little bit. All right. Guess what? Same thing as before. So bromine's going to come in and attack our more substituted one. We're going to end up re-attacking our bromine, and that's going to kick out the other bromine. I said bromine like 5 times in that sentence. So you end up getting, as your intermediate, so we have nucleophilic attack twice and then loss of a leaving group. All right, so those are those 3 arrows. First one, the bromine attacks the more substituted carbon. Then the less substituted carbon on your alkene attacks the bromine, and then the other bromine leaves, leaving you with this thing is called a cyclic bromonium ion. And we're going to see this is going to behave just like mercury. It's going to end up favoring the less substituted side And we're going to see that the more substituted side is going to develop more of a partial positive. And remember, it's able to do that because of hyperconjugation, right? More substituted, hyperconjugation stabilizes it more. So that one's going to be happy to accommodate more of the positive charge there on that carbon. And so our bromine, other bromine, bromide rather, was going to come in from the bottom and open up this ring, and we're going to end up getting ethyl group. So we end up putting a bromine on the other side. And this bromine is going to attack SN2 style, meaning from the back side. So if the first bromine came in and went on top, our other bromine is going to come in from the bottom and open up that ring, leading to the dihalogenated product with anti geometry. So those two will be anti to each other. All right, so we're going to end up with one on a wedge, one on a dash, if we were to look at this the same way. Let's take a look and see if we have, again, an example on Google. Yes. Okay, so here we go. Let's take a look at this one. This will be a nice, where's our, okay. So I want us to look at this particular thing here. So we see that this is nicely three-dimensional for us. We're going to have our bromide ion coming in from the opposite side that your original bromine came in from. If your bromine came in from the top, it's going to be sitting there on the top. And then it's going to, I've got an ad. Okay. It's going to then attack SN2 style from the back, from the opposite side that your original bromine went onto, and pop it open, and you'll get your anti product here. And of course you'll have it's an anti-mirror because it's a equal chance of top and bottom attack. So again, you're going to attack the one that is best able to stabilize the partial positive charge. So this is what we end up getting as our mechanism. Common solvent for this, by the way, CCl4, carbon tetrachloride, perfectly nonpolar solvent. That's pretty common here. So that's what we're looking at for this. So we have our bromonium ion that's made. Bromide attacks the more positive of the two, and you end up with the anti product there. All right, it looks just like the mercury one, except in this case, we're not going to get rid of the mercury one was Syn Addition because we end up now kicking out the mercury and another SN2 reaction. So we do two SN2s in the oxymercuration, demercuration. Cool. Next, another one. Y'all thought we were, I told you we have 14 reactions to cover, so we have so many more to go through. All right, so let me just do this one more time. So bromine comes in, attacks the alkene, alkene attacks the bromine, kicks out the other bromine, forming the cyclic bromonium. Bromide comes in from the opposite side of your bromonium and opens it up SN2 style, thus doing an anti-addition to our product here. All right, so next let's talk about halohydrin formation. Another very similar reaction. In this case, we also throw water in. And we're going to do another anti-addition. It's another anti-addition. And we're going to get the Markovnikov side hydroxy and the anti-Markovnikov. And this could be any halogen. You can do it with chlorine as well. But in this case, we're going to add onto the Markovnikov side, we're going to add a hydroxy. And on the anti-Markovnikov side, we're going to add a bromine. And those will be anti to each other. So do you see how many different things we can do with alkenes? It's wonderful. And the mechanism is going to be very similar to halogenation was. We're going to see that we're going to, first step, it will be the same. As before. Bromine attacks, gets attacked, kicks out its friend bromide. We end up with our cyclic bromonium. That one is the more positively charged side. The more substituted side is more positively charged because of hyperconjugation. And then our dearest friend water, with too many lone pairs, will come in and pop this open. And we will end up getting the opposite side, our hydroxy group. I'm sorry, technically it's OH2. Let's have another water molecule come over and grab that proton off. All right, and thus leading to our halohydrin. This is something called a halohydrin. So halo for halogen, hydrin for water. These will be important later on, next semester too, when we talk about epoxides. We're going to see it'll be a similar mechanism there. All right, so your water goes to the Markovnikov side, your bromine goes to the anti-Markovnikov side. So, are we good so far? Right now we're given all the tools for you to work on, and then we'll have problems to work on as well. So with all these reactions, super important to keep track of all the different reagents needed to make all of these different products. To add HBr, to add Br2, to add OH and Br, to add an OH to the Markovnikov side, to add an OH to the anti-Markovnikov side, to add an OH to the Markovnikov side with a carbocation. So many different things to keep track of. So I'll put up your practice today. I wonder if I should make that one an actual homework or not. I have to decide. But I'll put that up today, and you can start looking at it. So one way to do, sorry, we have a couple of more reactions to go over. Let's take a look at some. Dihydroxylation. We're gonna have a syn one and an anti one. We'll do anti first. Dihydroxylation. We'll put an OH on both of them. And whether that is anti or syn will determine the stereochemistry, right? In anti-addition, we'll have them on opposite sides. A Syn addition will have them on the same side. So we're going to see here that we have a couple to go over. Hi, Miss Bailey. Our first one, we're going to use something very similar to this. We're going to do another very similar type of reaction. We're going to use uh, what's called a peroxy acid. And we're going to end up getting an epoxide out. Epoxides are not charged, necessarily speaking, but they can be popped open just like our cyclic bromonium was with uh, an appropriate nucleophile. And fun stuff, we can actually have many different types of nucleophiles. Epoxides are isolatable, so you can stabilize them. If you just treat an alkene with a peroxy acid, you can do that. And then if you have some sort of nucleophile, you can end up popping that open and getting your OH anti. I'll put this one on the dash. So your nucleophile could be water. In that case, you get dihydroxylation. It could be an iodine. It could be a sulfur nucleophile. You have a lot of different nucleophiles you can do with this. You can also do an acid uh, acid catalyzed opening, in which case you're going to end up uh, getting the dihydroxy species. So let's go ahead. And again, this will be an anti-addition. All right, so very useful thing epoxides are. And we're going to see here that our nucleophile will attack just like it will before, attack the bottom side of our, or rather the opposite side of our epoxide, pop it open, and then typically you'll also need either a water wash or an acid wash afterwards, just to make sure that everything is protonated at the end. So we have a couple things we can do with epoxides. This is an epoxide. So with epoxides, let's look at how they form. A peroxy acid looks like this. This is our peroxy acid. Common ones, this is metachloroperoxy benzoic acid, or MCPBA. Um, this is probably the most common one you'll see. I'm okay if you just write RCO3H. So generic peroxy acid is fine. This one you will see probably pretty frequently, MCPBA. That is a peroxy acid. How the mechanism for this works is when an alkene comes in contact with your MCPBA or various peroxides, let's see how we make this. We're going to have, just like before, our dearest friend, the alkene, is going to act as both a nucleophile and an electrophile. We're going to end up attacking our oxygen. It's kind of terribly drawn. I'm going to have that come back in. That one's going to actually go on the other side. Or will it? This one will go to the more positive side. Yeah, no, we're good. And then kick out the leaving group. So just like with the bromine coming on. So although instead we're having something else happen here. As such, then we get our intermediate without the, we're going to forget about that. Our intermediate is going to have uh, kind of both of these things happening. Yeah, I'm just not even going to show that. We're going to end up with this. It's going to take off the proton itself, this carboxylic acid here. So we end up essentially just taking the, might be better to actually say that this bond is going to the hydrogen, and then the bonds between the hydrogen and the oxygen is going and latching onto our more electropositive carbon. So that would be the better way to do it. And then we end up losing our regular carboxylic acid. We end up making the epoxide, which should have two lone pairs. And just like before, we have the more positive side over there, or we can have a nucleophile. Say we are putting in, what nucleophile do we want to put in? How about Cn minus? Comes in, pops it open, and we end up with O minus, and then we'll need some sort of thing to stabilize this. So anti-addition. So some sort of nucleophile, whether it's a plain old nucleophile like cyanide, like iodine, like chlorine, whatever it may be, like bromine, we can get the opposite product here. Or we can just go ahead and use water instead. Can come in and pop that thing open, leading to the dihydroxy species. Oh my gosh. And then since we have these, I'm going to just do a proton transfer, and then poof, now we've done it. In reality, though, we would have the something would come on, take away a proton from the OH2 plus, and then in another step it would come on and put it onto, or then the O minus would attack it. But I'm just going to cheat and use the proton shift. So, ta-da. And so we'll end up dihydroxylating. So you can put an oxygen and a nucleophile, or two oxygens onto your molecule. So whatever your nucleophile may be. All right, and of course we will get the enantiomer. So we have a lot of fun stuff here. So we can put on many various nucleophiles. You can put alcohols. Let's see what nucleophiles we can use. Actually, I should show the acid catalyzed way first before we do this. So this would be neutral, not really the best kind of mechanism. In acidic conditions, let's have this be a base, actually. We'll just make this super easy. If we have a base, or rather, the hydroxide comes in, and then we just need to protonate this thing, and then there we go. We'll make this just a little bit easier for us. We regenerate our base at the end. In acidic conditions, though, conditions, we're going to see the mechanism is a little bit different. for the epoxide. And let's say we use methanol and acid. Let's say we use HCl and methanol. Let's see what we're going to get. The first step here is we're going to protonate our oxygen here. And let's use sulfuric acid actually, because sulfuric acid is non-nucleophilic. Chlorine can be nucleophilic, so we're just going to make this really obviously non-nucleophilic. Okay, there we go. So, although really it's going to be protonated methanol, whatever, let's just go ahead and do this. So we end up with the positively charged one here. And we're going to explore this more next time. For right now, I'm just going to be consistent. I'm going to lie to you. And say we're going to go ahead and just attack the right side of this molecule, the one that's more positive. In reality, though, the sterics are going to come into play, and we're going to say that that side is not going to be attacked, but that we're going to cover next semester. So we're just going to, I don't want to lie to you, though, but this really is stuff that we're going to cover next semester. So we're just going to be consistent, okay? Methanol comes in, pops it open. And then another methanol comes along and closes it down. You get your OH and your methoxy group on anti to each other. Although in reality, you'll probably have it attacking from the steric side. So there's always a balance between sterics and electronics, right? That tertiary carbon, we'll say it's tertiary, it's tertiary, has more positive character. So electronically, that's a more favorable position. But those two methyl groups may make it difficult to do an SN2 type attack, right? Because that's now a tertiary carbon. We're not likely to do SN2 on a tertiary carbon. So there's always a trade-off here. So for right now, I'm going to say we're going to go with electronics all the way. Next semester, we're going to focus on dealing with steric effects too. All right, so just go ahead and right now, nucleophile will attack the electronically better carbon. So we'll focus on that later. All right, so it's going to go ahead and attack, and then we can go ahead and use our methanol. All right, so various nucleophiles can be used. Nucleophiles, we've got X minus, CN minus, sulfur nucleophiles, alkoxides. These would all be more for basic conditions. Or neutral conditions. For acidic conditions, you can use X minus again. You can use water and alcohol. These are probably the more common ones you'll see here. So standard nucleophiles, right? You can also have OH, of course, for your basic conditions ones. So you can see you can get a lot of different things to end up Why did I put counter ions with some of them but not with the others? There we go. Typically with the neutral or basic ones, you're using stronger nucleophiles. With the acidic conditions, you're typically using weaker nucleophiles. Um, doesn't really matter. So HX would work. That's why I didn't want to use HCl, because you're going to end up having Cl minus, which could then just come in and attack as well. So there's always side reactions happening that we must be aware of. So we can have various nucleophiles here that can pop open your epoxide. So if you want anti-hydroxylation, though, either use OH minus or H2O on your epoxide, and you will get the anti-hydroxylated species. So let's recap this. If you use MCPBA or some other peroxy acid, and then use NaOH, for example, you will get the dihydroxylated species. Or acidic water. Usually the acid is going to be sulfuric because it's not nucleophilic. And you get the enantiomer as well. Alrighty. Another one. What about Syn hydroxylation? What if we want them to be on the same side? We're going to use an osmium-based compound and then a reducing agent. And we're going to end up getting a Syn hydroxylation. So OSO4 is osmium tetroxide. Or we can say, if we're going to be really good chemists, osmium 8 oxide. Because osmium is a transition metal. We're going to draw it covalently. That's what it looks like. Osmium atom in the middle, 4 oxygens. This is a pretty terribly toxic thing. This reaction is not really used much anymore. There are other ways to do it, but typically it's a good way to do it. So let's go ahead and take a look at what's happening here. And I'm going to redraw my thing a little bit sideways because we're going to see we need that here. So I keep doing that. All right, so just like before, we're going to have one of our oxygens attack the other oxygen, and we're going to go ahead and put our electrons onto the osmium, giving us species. Again, this is plus minus. We could have them on dashes as well. And then you just need a reducing agent to cleave it off. So you use a reducing agent like the sodium sulfite there, and then that cleaves it off. We don't have to worry about the mechanism for this, but we need the reducing agent, such as sodium sulfite. And then you need water to protonate your alcohols. And you'll end up getting them. So, fun stuff. There are other ways you can do this. Pretty common one, though, historically speaking, was to use osmium tetroxide. And there are now like kind of better ways. You can use less osmium because the osmium is terribly toxic. It's an interesting metal. I think it's the most dense or second most dense metal. I forget, but it's pretty cool. So osmium we don't really see much of, and we can use other ones like permanganate in basic solution. We'll also get this to happen if it's cold as well, typically, and it's going to form a very similar type of complex. If we use do it upside down this time. If it's cold and basic, you will end up with Syn hydroxylation as well. And I'm going to put them as dashes this time. So you'll get the same sort of product out, and it looks very much the same. You have MnO4 kind of sandwiching on, and then you'll have your bases to kick it out. And so the sort of oxidation can work there as well. So you can end up with dihydroxylating your thing if it's cold and basic. All right. So we're almost through. This is all of our additions. I say that as we've done like what 10 or something additions to alkenes. We've done halogenation. We've done hydrohalogenation, both Markovnikov and anti-Markovnikov. We've done hydroxylation, both anti-Markovnikov and Markovnikov, and also Markovnikov with carbocation. We've done Halohydrin formation. We've done catalytic hydrogenation. We have done dihydroxylation, both syn and anti. We also saw that we could make an epoxide and do other things with it. So we could put on other nucleophiles to our epoxide. Wow. Makes you want to cry, doesn't it? All these reactions. There are a lot of them. 14. All having their own reagents, all giving different stereochemical and regiochemical outcomes. So make index cards, make flashcards of these. You're going to want to be able to identify right away by the reagents what type of reaction you have. Is this thing going to be a Markovnikov addition if it's adding one thing? Is this adding two things? Are those things anti or syn to each other? There's so much to think about. And this is just additions. We have other things we're going to do. We're going to talk about oxidative cleavage next time. And then we'll do some problems. So we have a lot to do. All right? And there's a lot of reactions here. So if you want, if y'all say so, we can do a spectroscopy review on Friday. Otherwise, I'll just leave you to it. And then maybe we'll do one next Friday or something. We'll see. So remember, these alkene reactions are not on your next exam, because I want you to focus on spectroscopy and radicals. All of these alkene reactions will be on your fourth exam, right? As well as alkynes and alcohols. So we have a lot of stuff for our last exam. All right? So that's it then. That'll be it for today. So tomorrow Monday, Monday, we'll continue on do the rest of these, and then we'll start alkynes. So fun stuff. All right, awesome. All right, take care. See you next time.